Let's go over some definitions for elements in the periodic table. For each element in the periodic table, we will get quadrants like this here, which contains information about the element. The first one is a whole number, defined as the atomic number. This is a letter Z and is the number of protons in the atom. For the case of hydrogen, this has one proton. Then we have the letter H, that is the symbol for the element, the name of the element, and then a decimal number that is the atomic weight in units of atomic mass number, AMU. This is represented with the letter A and is the number of protons and neutrons in the atom. So for the case of hydrogen, this is protons plus neutrons. So these can be approximated to the closest whole number. So in this case, it's equal to 1. So we know that there is 1 proton. So there must be 0 neutrons for this to hold true. So the number of neutrons for hydrogen is 0. Okay, and then we have the electron configuration, which we will talk about later in these lectures. So here we have the orbit model of the hydrogen atom. We can see that at the nucleus it has 1 proton and 0 neutrons. So 1 proton and 0 neutrons. And we also have an electron orbiting around the nucleus. So for all elements, something that must hold true is that the number of protons and number of electrons must be equal. Otherwise, this would be a charged particle. But for it to be neutral, this has to hold true, which is the case here in hydrogen. So this particular hydrogen that has 0 neutrons, 1 proton, and 1 electron is called protium. Protium can be written in other ways as symbols, where H has a 1 and 1 as superscript and subscript. So this upper one is the atomic weight, and this lower one is the atomic number. Notice that this is the other way as the one in the periodic table. Or this can also be written as just 1 as a superscript. And this would be the letter A for the atomic weight. Having these concepts in mind, let's talk about isotopes. Isotopes are variants of an element which differ in neutron number, and consequently in atomic weight. Let's look at the 3 isotopes of hydrogen: protium, deuterium, and tritium. We can see in the orbital models that protium has 1 proton, and so do the other 2. But the number of neutrons in protium is 0. Deuterium has 1 neutron, and tritium has 2 neutrons. So they all differ in number of neutrons. That's what makes them isotopes. Now let's analyze their atomic number, weight, and abundance. Starting with protium. So the atomic number is the number of protons. This is equal to 1. We also know that number of protons have to be equal to number of electrons for it to be neutral. The atomic weight is protons plus neutrons, and this is equal to 1. We know that proton is 1, so neutron has to be 0 for this to be equal to each other. So we have 0 neutrons. The abundance of these is 99.985%, which is pretty high. Now, what makes protium what it is having 1 proton, 1 electron, and 0 neutrons. Alright, looking at deuterium. Deuterium, the atomic number is number of protons, which is 1. The atomic weight is protons plus neutrons, and this is equal to 2. So we have 1 proton, so there must be one electron, one neutron. So neutron is equal to 1. The abundance for this is 0.015%. So what makes deuterium what it is having one proton and then one electron to keep neutrality and one neutron. Okay, for tritium, the atomic number is still 1, and this is the number of electrons. The atomic weight is proton plus neutron, and this is equal to 3. Proton is 1, so number of neutrons has to be 2. And the abundance for this is less than 0.001%. Okay, so what makes tritium what it is having one proton, one electron to keep neutrality, and 2 neutrons. Okay, so we can see that the 3 isotopes of hydrogen have the same number of protons and electrons, but they differ in number of neutrons. In the symbolic form, we can check this also quite rapidly by knowing that the first number here is the atomic weight, and the second number is the atomic number. And this one is the atomic weight as well. So we can see also that A is equal to 1, and this is the number of protons plus neutrons is 1 plus 0 equals 1. This one is equal to 2, proton equals 1, neutron equals 1, they add each other out, so it's equal to 2. And here, proton 1 plus 2 neutrons is equal to 3. Okay, now let's look at another example, the isotopes of carbon. Let's look at the atomic number, atomic weight, and the abundance of these. Okay, so we have the atomic number for carbon 12, that's the number of protons, so that would be 6 for this one. The atomic weight is protons plus neutrons, which in this case is 12. So if we have 6 protons, then we must have 6 neutrons for it to be 12. So number of neutrons is 6. The abundance for this one is 98.90%. And the abundance is just numbers that I'm giving you. Okay, so what makes this carbon 12 is having 6 protons, then the same number of electrons for charge neutrality, and 6 neutrons. Okay, looking at carbon 13, atomic number of protons is equal to 6, atomic weight, protons plus neutrons is equal to 13. So we know number of protons, to have 13 we need 7 neutrons. So number of neutrons is equal to 7. And the abundance of this is 1.10%. Okay, so what makes carbon 13 is 6 protons, same number of electrons for neutrality, and 7 neutrons. Alright, looking at the last one, carbon 14. So the number of protons or atomic number is still 6. Atomic weight is 14. So we know that we have 6 protons, so we need 8 neutrons. And the abundance is less than 0.01%. Okay, so what makes carbon 14 is having 6 protons, same number of electrons for neutrality, and 8 neutrons. Perfect. So looking at all 3 isotopes of carbon, they all have the same number of protons and electrons, equal to 6, and they differ by number of neutrons. So that's what makes them isotopes. Perfect. Let's do some more practice problems about isotopes. The problem here says, give the number of protons, neutrons, and electrons in an atom of boron 11, boron 10, phosphorus 31, and uranium 238. Okay, and we have the periodic table here on the left to help us identify important numbers. Let's start with the first one, boron 11. So the 11 here, as we remember from the carbon isotopes, is the atomic weight. So that is protons plus neutrons equals 11. Then we have to look at the periodic table, and we see that boron has a 5 on the top. That is its atomic number. So an atomic number is the number of protons. That is 5. So if there is 5 protons, that means that there must be 6 neutrons, because protons plus neutrons equals 11 for this case. Okay, now we remember that there must be equal number of electrons and protons for it to be neutral. So boron 11 has 5 protons, 5 electrons, and 6 neutrons. Next we have boron 10. So the 10 is also protons plus neutrons equals 10. Looking at the periodic table, number of protons is 5, number of electrons is 5 as well, number of neutrons has to be 5, so that protons and neutrons equals 10. Perfect. For C we have phosphorus, (31), and again the 31 is protons plus neutrons equals 31. And then looking at the periodic table, phosphorus is located right here, has a 15 for atomic number, so it has 15 protons, so there must be 16 neutrons for it to be 31. Protons plus neutrons equals 31. And for charge neutrality, protons and electrons are the same, so 15. And this is the answer for phosphorus 31. Now the last one is uranium 238. And 238 is the number of protons plus neutrons, is the atomic weight. Then we find in the periodic table where uranium is, and let's see, uranium is located right here, is a 92. So protons is equal to 92, and then so if we have 92 plus neutrons equals 238, so the number of neutrons has to be 146, and then electrons is same as protons, so 92. So this is the answer for uranium 238. 92 protons, 92 electrons, and 146 neutrons. Let's do one last problem regarding isotopes. Here it says to complete the following table. So the first one is chlorine 36. I will do my scratch work here. So for chlorine 36, the 36 is the atomic weight, which is protons plus neutrons. Then we can look directly at the periodic table and we find that chlorine has an atomic number of 17. So that's the number of protons. So writing that here, the number of neutrons has to be equal to 19. And for this chlorine to be neutral, number of protons and electrons has to be equal, so 17. So let's fill out this table. Number of protons is 17, neutrons 19, electrons 17, and this is chlorine. And the mass number is another name for the atomic weight or atomic mass, so that's 36. Okay, moving on to the next one. So the next one, we're given the number of protons is 30. So this is equal to the atomic number. So we can see directly in the periodic table that that belongs to zinc. So this is zinc with 30 number of protons. So protons plus neutrons equals, and then we see that for mass number or atomic weight, it has 65. So this is zinc 65, and then if number of protons is 30, then number of neutrons is 35. Okay, so filling this out, neutrons 35, and then number of electrons has to be equal to protons 30, and this is zinc 65, and zinc for the element. Okay, then the next one has 20 neutrons and 20 electrons. So the number of electrons has to be equal to the number of protons, 20, and this is the atomic number. So we can see directly in the periodic table that 20 belongs to calcium. So calcium, and we see that the number of protons plus neutrons equals 20 plus 20, 40. So this is calcium 40. So this belongs to calcium. And then the atomic weight is 40. Protons plus neutrons. Perfect. Now the last one is lanthanum. So we're given that the number of neutrons for lanthanum is 80. Okay, so neutrons equals 80, and then we can look up in the periodic table the number of electrons or protons, 57. So protons is 57 and same number of electrons for this to be neutral, 57. And then the atomic weight, which is neutrons plus protons, is equal to 137. Okay, so filling this out, this is lanthanum 137, and number of protons is 57, electrons is the same 57, and mass number 137.